Welcome to this explainer, where we are going to unlock the notoriously complex, almost superpower-like clinical skill of arterial blood gas interpretation. Today, we're basically acting as physiological detectives. We're going to read the hidden metabolic stories of our patients, written entirely in the language of partial pressures and ion concentrations. Let's get into it.
Okay, let's dive right in by confronting a pretty dramatic reality that was articulated by early 20th century physiologists. Life is a struggle against hydrogen ions. Now, I know that sounds like an exaggeration, but it is the absolute central truth of acid-base physiology. Every single breath you take and every heartbeat you make is fighting this exact war.
And this number brilliantly illustrates the incredibly high stakes we're dealing with, 0.4. See, the entire machinery of human cellular life is calibrated to operate within an extraordinarily narrow pH corridor of barely 0.4 units. We're talking specifically about a pH of 6.8 to 7.2 at the cellular level. If you step outside that tiny window, proteins denature, enzymes just cease to function, and well, life essentially fails.
Here's our roadmap for today. We're going to cover 1. The struggle against hydrogen, 2. Decoding the ABG machine, 3. Gaps and hidden acids, 4. The compensation rules, 5. The Stewart model explained, and finally, solving the clinical mystery.
All right, part 1, the struggle against hydrogen.
To truly understand this struggle, we really need a high-stakes case to anchor our investigation. So, we'll be solving the mystery of patient C. This is a 19-year-old with type 1 diabetes who's been vomiting for 2 days straight. They present with a severely dangerous pH of 7.08. Their breathing is incredibly rapid at 32 breaths per minute, even though their oxygen saturation is totally normal on room air. To save this patient, we need to build our forensic toolkit piece by piece.
Moving on to part 2, decoding the ABG machine.
Now, what's really interesting here is the illusion versus the reality. We tend to look at an ABG printout and treat every single number on there as hard, measured data. But the reality? The machine only measures 3 parameters directly: pH, PaCO2, and PaO2. Everything else, including bicarbonate and base excess, is merely a mathematical calculation based on the Henderson-Hasselbalch equation. The machine doesn't actually measure bicarbonate, it just infers it.
Which brings us to part 3, gaps and hidden acids.
So, the crucial point is that to find these hidden acids, we have to rely on a fundamental law of physics, electrical neutrality. In any aqueous solution, like human plasma, the total positive charge must exactly equal the total negative charge. Because of this, we can look at what we routinely measure: sodium on the positive side and chloride plus bicarbonate on the negative side. The difference between them is our anion gap. This gap, which is normally around 8 to 12 milliequivalents, reveals the footprint of hidden unmeasured anions, or acids, in the blood. Things like albumin, phosphate, and potentially dangerous pathological acids.
When we calculate that anion gap, it acts as a signpost telling us exactly where to look next. If that gap is elevated, meaning unmeasured acids are taking up extra space, we have a high anion gap metabolic acidosis, or HAGMA. We use the MUD piles acronym to hunt down the culprit, things like lactate, ketones, or toxins. But if the gap is normal, meaning the acidosis is just from a loss of bicarbonate that got replaced by measured chloride, we have a NAGMA. For that, we look to the hard up acronym to see where that bicarbonate was lost, pointing to things like diarrhea or renal issues.
Okay, part 4, the compensation rules.
Once we identify the primary disturbance, we absolutely must determine how the body is fighting back. To do this flawlessly every single time, we need a system. By strictly following the 6-step framework, we can uncover complex, mixed disturbances that are super easy to miss when you skip clinical steps. We look at the pH, find the primary disturbance, assess the compensation, calculate the gap, check the delta-delta ratio to sniff out any hidden third disturbances, and finally, assess oxygenation.
And to properly execute that compensation step, we use established bedside mathematics. A really cool novel application of the Boston rules even breaks this down further into a stepwise approach. It calculates total changes in pH by separating the respiratory components from the non-respiratory or metabolic components. It lets us mathematically isolate exactly what the lungs are doing versus what the kidneys and cellular buffers are doing.
Think of these compensation formulas as your physiological lie detectors. They allow us to calculate exactly where the expected compensatory values should be. For instance, If bicarbonate drops, the lungs should hyperventilate to lower the CO2. If we plug our patient's bicarbonate into Winter's formula, that's 1.5 times bicarb plus 8, it tells us exactly what the CO2 should be. This brilliantly proves if a second primary acid-base disorder exists, because if the actual numbers on the printout don't match our math, there's another primary problem hiding in plain sight. Next up, Part 5, the Stewart Model Explained.
As our detective work deepens, we eventually hit cases where traditional rules kind of fail us, which brings us to the paradigm-shifting work of Peter Stewart. Stewart asked a brilliant question: what actually determines the pH? He shifted the entire focus to the strong ion difference, or SID. He revealed that strong ions, like sodium and chloride, are essentially chemical spectators. Their charge imbalance literally forces the weak buffer systems, like bicarbonate, into position, which determines the final pH. The strong ions set the electrochemical stage. Now, here's the truly revolutionary claim of Stewart's model. We are traditionally taught to treat bicarbonate as a primary driver, right? But Stewart proved that bicarbonate is not an independent driver of pH at all. It is rather a dependent consequence of three true independent variables: the strong ion difference, the total weak acid concentration, and the partial pressure of CO2. Bicarbonate just goes wherever these three variables force it to go.
And this perfectly explains clinical phenomena that traditional models really struggle with. Take for example, why infusing large volumes of normal saline causes a metabolic acidosis. Saline has an SID of 0. Its sodium and chloride completely cancel each other out. So when you infuse it, it dilutes the body's normal electrochemical SID of 40 downwards. This lower SID forces the weak buffers into an acidic equilibrium, dropping the pH. It literally causes acidosis without adding a single drop of acid.
All right, the final act, Part 6, Solving the Clinical Mystery.
Let's bring it all back to patient C and apply everything we've just learned. Our 19-year-old diabetic patient has a profound primary metabolic acidosis with a terrifyingly low pH of 7.08 and a bicarb of 5. By using those Boston rules, we calculate their expected PaCO2 should be around 15.5. Their actual PaCO2 is 18. This confirms that their rapid breathing is an appropriate, nearly maximal respiratory compensation.
Next up, we calculate the gap. Assuming normal sodium and chloride, their anion gap is sitting at a whopping 30. This reveals a massive hidden acid load, which, given their history of type 1 diabetes, points directly to diabetic ketoacidosis. We then check the delta-delta ratio, which comes out to 0.95. This proves beyond a shadow of a doubt that this is a pure high anion gap metabolic acidosis. The vomiting they experienced hasn't caused some hidden secondary alkalosis. The keto acids are entirely responsible here.
So, we've cracked the case. We now know that wild respiratory rate of 32 is a desperate physical mechanism to blow off acid, classic Kussmaul breathing. It's not driven by hypoxia at all. And most critically for treatment, because severe acidosis dynamically shifts potassium out of cells, we absolutely must replenish their potassium before giving any insulin. The severe acidosis is dangerously masking total body potassium depletion. If we were to just give insulin first, the potassium would crash, triggering a potentially fatal arrhythmia.
You now possess the tools to read this hidden language. From the Henderson-Hasselbalch mathematical illusions to the Boston compensation rules, right down to Stewart's electrochemical stage. Because really, every single blood gas is just a snapshot of a physiological conversation. So the final question is, how are you going to use this physiological forensic accounting to decode your next patient's story?